It's hard to wrap your mind around like just how powerful JWST is. Obviously for all of that extragalactic stuff, but for studying exoplanets, studying the atmospheres of exoplanets. For the first time, astronomers have just this incredibly powerful tool in their hands they can use to examine the atmosphere of a planet orbiting another star. Incredible. And yet we are starting to learn a tremendous amount about these exoplanets and starting to have what were long-standing questions start to get answered. It feels like every week new chemicals are being found in exoplanetary atmospheres. So to talk about this with me today is Dr. Luis Welbanks. He is a NASA Hubble Fellow at the Arizona State University, and he specializes in exoplanet atmospheres. He was part of the team that studied that methane in the exoplanet that we talked about in one of the previous interviews. And so we have a very deep dive into specifically how JWST is able to make these exquisite observations of gases in the atmospheres of exoplanets. And sort of, we talk a bit about the philosophy of what it's like to be a scientist who is trying to help us answer that question, are we alone in the universe? Understanding the ramifications of what answers you give and how that will be received by society. So enjoy this fascinating conversation with Dr. Luis Welbanks. Luis, how good of an exoplanet atmosphere detection tool is James Webb?
I would dare to say that it is the best thing we currently have. That will perhaps rob some people off because obviously we can do a lot of great science from the ground. But just by mere virtue of how many wavelengths it can observe, and the fact that we can look at several species, several bumps from several species at the same time, that just makes it exquisite in my view.
So, I mean, let's talk about, because when we think of JWST, we think of it as a tool for studying the farthest reaches of the universe, these highly redshifted galaxies that are forming just a few 100 million billion years after the Big Bang. And yet, is it just like, why is it so naturally also good at studying exoplanet atmospheres? Is it just
Yeah,
like a bizarre coincidental overlap between capability, infrared?
I think a lot of great people did a lot of great lobbying to convince the galaxy people that it's also great to look at planets. And I think that the fact that you can look at very cold, far away things, and we need to look at that in the infrared. And it also happens that these wavelengths are what we need to observe at the planet at these other wavelengths where we know that there is multiple absorption features by several gases that we're interested in. That is where the coincidence slash not so much coincidence happened. The fact that the same wavelengths we can use for very interesting science for exoplanets.
And so, as a person who is extremely interested in the capabilities of the telescope for exoplanet study, give me your perspective of the telescope, instrument by instrument capability, and how it maps onto the kinds of work that you're trying to do.
The amazing thing about JWST is that with every single instrument that it has on board, we can answer specific questions. So it's almost like every single instrument is designed for some very specific science case that we may be interested for planets. But also, we are starting to see the power and the beauty of putting every single instrument together and really appreciating the beauty of almost seeing everything everywhere all at once. For example, there is Prism, which is part of NearSpec, one of the instruments on board, and that gives us the broader wavelength coverage. It's about, I would dare to say, a little bit below 1 micron, 0.8 to past 5 microns, which is much more than we previously had with the Hubble Space Telescope. So the beauty of seeing a planetary spectrum in one shot across so many wavelengths, that is outstanding. But it has some issues. Sometimes it saturates. It may not be very good for for some stars that are very bright. So then what do? Then you may want to look at instruments that are better at looking at very bright things like NIRISS. NIRISS gives you a little bit less of a wavelength, but it covers from like about zero point 0.8, a little bit below, to 2-ish microns. So then you can see a lot of wavelengths where we expect water to be present. We have MIRI. MIRI goes from 5 to 12, and in some modes it can go up to 20 microns or so. So then we're going past anything that we had previously seen, and we're starting to see a lot of interesting physical and chemical processes, like species that we perhaps expected but we hadn't seen before, or processes with clouds. And by putting the puzzle together with several pieces, we get to see how all these wavelengths communicate with each other and give us a multidimensional view of the planet.
So give me an example. Like, let's say that you have a new target, some planet orbiting some star, and you want to understand the atmosphere as best you possibly can. What is the sort of, how would you approach this problem using JWST as your instrument?
Yes, the key point here is, first, what science question are we trying to answer? For instance, are we trying to be very smart with our use of resources and at the 0th order figure out whether the planet has an atmosphere? So maybe before shooting it with every single capability that we had on board of the telescope, let's look at it at a particular wavelength where we would expect this would help us understand whether there's an atmosphere or it's a bare rock. Lo and behold, that's what people have done with TRAPPIST, right? They've looked at it with MIRI at a particular photometric point so that it helps us distinguish whether it has an atmosphere or not, to inform how much time we should spend moving forward. Another example would be, okay, we have a cool planet. Let's figure out whether it has methane and water, because we're interested in that combination of chemical species for reasons. Let's say that we want to understand the processes of chemical equilibrium. So we better use instruments that allow us to observe the wavelengths where we know that methane and water absorb. And we want to make sure that there's no gaps or no offsets between the detectors. So maybe for that science case, the best thing to do is let's look at it with NIRCam, which goes from 2 to 5 microns-ish. So we would get a little bit of water, we would get methane, and we can also get other carbon species like CO2. So we can answer these questions about chemical equilibrium. And as a byproduct, we could get information about the carbon inventory and the oxygen inventory. So we can say something about the carbon to oxygen ratio and link that to our understanding of perhaps how planets form. Or maybe yeah.
Oh, I was going to say, like say you did want to make that first initial, does this planet have an atmosphere or not question. Is that a relatively quick task for Webb?
I guess it depends on how quick do we want it to be.
Yeah.
I would say yes-ish, in the fact that JWST has been launched now for 2 years. It's been operational for, well, actually, it's been launched almost 3 years, 2 years of operations. And in that much time, we have an answer for the first 2 TRAPPIST planets, B and C. So I think that is interesting, right? But obviously, there's still excitement, and there's other questions about, could this be from the star or whatnot? So it is very helpful, and it can do that very quickly and give us a first look at planets and motivate further science after the fact.
And then you mentioned this idea of like more comprehensively examining one planet. And this is one of the projects that you're a part of. So can you explain the goal of this?
Yes. The early release science program for transiting exoplanets with JWST, it's a large community effort. I would dare to say that there are over 150 exoplanet scientists working all together on this project. And the spirit of the project was to observe a planet with with every single instrument on board of JWST, to provide the community with the tools and the knowledge to use a telescope. So provide open source mechanisms, open source software, templates, so that they can know how to use it for further observations. And the planet that was selected was WASP-39. There was a long process before the telescope launched. about thinking of the best targets and reshuffling based on the delays that the telescope had. And as a byproduct of also giving a lot of tools to the community and a lot of observations for everyone to use, we are getting also the first comprehensive look at an exoplanet. We're getting the first spectrum of a planet from zero point 0.5 to 12.5 microns with every single instrument on board of JWST. And we're learning about the kinks, the little things that we need to iron out when studying an exoplanet.
Right. I can just imagine all of the best practices about crunching down the data, about managing the data pipeline, about like just everything. I can just imagine. So, I mean, would you say that we know more about WASP 39b than really any other exoplanet out there at this point?
Yes, I would dare to say that. And it's so beautiful because in the process, we've also learned a lot about ourselves. And that
you
was
mean as
not
astronomers or as a planet?
as astronomers for sure.
Yeah.
Because it's been so fun and challenging to bring everyone together, and people that now have decided to share their ideas, share their knowledge. And Billy Bob has a particular model that they've been using in Europe, and Sally Sue has been using this model in Canada, and everyone's thinking like, oh, my model is the best, or my model brings this to the table. How do we put all this knowledge together? And by trying to study a planet in so much detail, we're also developing the language to communicate with each other and talk about what do we mean when we talk about chemical equilibrium? What do we mean when we talk about a detection? All these, what do we mean as a field to really push the field forward and make sure that our science is reliable and robust? That is what I mean, that it has allowed us to learn a lot about ourselves. It's like putting a mirror to ourselves and look at the beautiful and not so beautiful things. Like, okay, how do we do this together? How do we come together as a field and present something to the community?
So, and I guess part of the problem is that there are well over 5,000 exoplanets known so far, way more than that, candidate planets. It's just one space telescope. It's oversubscribed by the entire astronomical community. You definitely need to show up organized if you want time on that telescope.
Absolutely. It's a great opportunity and a great responsibility because allow me to be pessimistic for a second, right? Imagine that we spend so much time looking at this planet with every single instrument, and then we cannot say anything useful. What would the future of the field be? What would the future of exoplanets be? Well, we cannot learn anything, even with our best observations. So that is a great challenge and a great opportunity to rise to and say, actually, no, this is how we can have a manual of sorts to use the telescope, the best practices, and the lessons learned. This is where we went astray. This is where we actually learned something better.
Yeah, and I know there's another project that I actually interviewed one of the people who was coordinating this, where you're coming up with an overall criteria on you're sorting the planets into various tiers and using that as a way to, as a priority list. Like, let's start with the most interesting planets first with that precious time that we have on this amazing telescope. So, I mean, if we know more about WASP 39b than any other exoplanet, tell me about this planet. What do we know about it?
Well, the results are currently in prep, and some of them have already been out. So I can talk a little bit about both. We know that this planet has multiple chemical species that we can see with our bare eyes. No modeling needed. You see a bump. We see bumps that we know correspond to water. We see bumps that correspond to carbon monoxide, carbon dioxide. It was the first detection of sulfur dioxide in the field, which is a product that caught many of us by surprise. And many others were like, oh, obviously it's going to be there, which is a product of photochemistry. There's inferences of how this planet actually has inhomogeneities. It's not a solid ball of gas that looks all the same. There are actually patches in the way the clouds are covering the planet. It has strong lines of sodium and potassium. And all of this information together, when we try to understand what this means, we understand also about the bulk composition of the planet. We know what sort of metallicity it has. That is how enriched it is in its chemical composition. And we can say that if we compare that to the composition of our star, the sun, is it above or below that? And it seems to be more enriched than our sun. So that is also interesting.
And now that you know so much about this planet, how does that compare to what you wish you could know about planets? Like, I think you're in being able to use JWST so exquisitely, you're starting to run up against what its limits are as well. And so where are you starting to find that, okay, you know what? These are the range of questions that we can answer, and this is the future that we're still going to have to get a new telescope to figure out.
Yeah, the future has truthfully and rightfully been identified in the reflected light of smaller planets and Earth-like planets around Sun-like stars, and a lot of the science that the Habitable Worlds telescope is going to be doing. I think, truthfully, JWST has been having some challenges with the small planets, and there's a lot of science that will come up in the next few years that I hope proves me wrong and shows that actually we can do it and we don't need another telescope. But so far, that seems to be the challenge: pushing the envelope to the smaller planets around big stars, and even the smaller planets around small stars, and how do we account for the effects of the star. And given that it's a new toy that we're playing with and we're learning about, we're learning also about how to treat the data, how to interpret the data, and whether we have some systematics or some nuances in how we interpret. Um, as a modeler, for example, I'm very interested on if we see a little peak in the data. Is that because micrometeorite hit the mirror, or because actually there's a little peak in the atmospheric spectrum that we should be fitting for? And understanding whether we have missing physics that will push the field forward, or we have missing understanding of how the telescope operates. And either way, we need to answer that now so that we have a clear path forward towards utilizing and maximizing JWST, and know what we need to look for with habitable worlds and ground-based facilities.
Now, you mentioned earlier on that we know a little bit about the TRAPPIST-1 planets, and these are like the most interesting exoplanetary worlds that we know of so far. The first two seem to be airless, and we're waiting on the rest of those planets, and it has been a while since that data has been gathered. First, like, does that data exist somewhere? Like, have detailed scans of any of the additional planets, especially the ones in the habitable zone, has that data been gathered?
I believe so, yes.
Okay.
And some lucky few have seen it, and some lucky few have presented it at conferences, and some of us have witnessed some of the spectral preliminary work. And I'm very excited about it.
Oh, I should have been at that conference then.
Next time I'll send you pictures.
Yeah. But I mean, I think, but like a lot of people are wondering why it's taking so long. Why do you think it's taking so long?
Well, I think it's not an easy feat, right? We are truly pushing, and I'm using the royal we here. We as a field, we are pushing the field and the capabilities of our models and our ability to process the data. And we are learning something new about this telescope. So perhaps not, I cannot specifically tell you about TRAPPIST-1c DE, but from other targets, we know that sometimes the assumptions that we make in processing the data, how do we go from the raw CCD pixels to the squiggly lines that we try to fit, changes based on some of the assumptions on who is processing the data. So that rigorous process of science takes some time. And I think people have been really good about being thorough, because, again, we want to make sure that we don't fumble and say something ridiculous early on.
Right. Well, imagine that you have no idea and you haven't looked at the data yet. I'm speculate, based on the conversations that I've had with astronomers so far, that if there was no atmosphere there, we would have heard that. And that there is so much concern in the astronomical community about saying the detections of various chemicals have been found in the atmospheres of various worlds. Think about the discovery of phosphine at Venus, methane at Mars. Like, there is inconclusive results that have come back to haunt astronomers later on, and that any discovery, even if it's mundane and boring chemicals in the atmosphere of a world in the TRAPPIST-1 system, is so interesting, and yet is at the limits of detection of this telescope, that it's making the data analysis a very cautious, careful process. And anybody who is going to be announcing these results knows that they're just going to get torn apart by their colleagues, and they need to make sure that their conclusions can sort of withstand that. Does that sound accurate to you?
It sounds feasible. I think it
Okay, all
sounds
right.
like an educated guess. But
Yep. Yeah.
think about the other scenario. What if, and I'm not saying this is the case, what if we spent 2 years of JWST and every single one of the planets in TRAPPIST are bare rocks? At
Yeah.
least with JWST, we cannot say anything. And we're like, well, it seems to be flat. It's a flat spectrum.
Yes.
How would that be perceived by the public? How would that be perceived by the rest of the astronomical community?
Yeah.
Like,
I mean, I
then
think it would be disappointment. Like, I think we were hopeful, but reality doesn't give us what we want. And I think scientists underreport null results when they should do more. I think it's perfectly fine to say we didn't find anything. I'll write a story about it, right? I will interview someone about it. We scanned hundreds of worlds. We didn't find anything. What are you going to do? I think that's okay.
Yeah. And the other thing is that, to the best of my knowledge, not every single observation has been executed.
Right. Oh, really?
And
Okay.
maybe some of them got executed a couple months ago. So you have a piece of the puzzle with one instrument, and you're like, oh, this looks tentative. And then you are waiting to get the other piece with another instrument. You're like, oh, okay, well, how does that affect things? I know of some programs, and there are some in the literature, where they look at a very interesting target. They shoot at it with the telescope, and there's a bump. Wow, we found, I think this one was laughing gas, N2O. And they shoot at it again 6 months later, and the feature is not there. And they did a great job of reporting it and how it was there, it wasn't there, and trying to explain why. But maybe something like that can happen with other instruments, with other planets, and TRAPPIST could be one of those.
I mean, one of the things that's been really interesting to me is how definitive the absorption lines that we're seeing in these atmospheres are from JWST. Like, what we saw with Spitzer and other various infrared telescopes was these faint hints of atmospheric gases. And now it is just absolutely conclusive. There is no question that there is water vapor in the atmosphere of that planet, or carbon dioxide, or whatever. And that must feel really satisfying.
Yeah, and that is very exciting, but that is also shaping the way that we do science. I am particularly frightened and excited about how do we go about claiming detections. What does a 5 sigma detection mean? And I think it's very nice when someone who has been trained on these methods get to recognize the CO2 bump, and you're like, whoa, there's a big feature there. Something is happening there. But not every gas has a CO2-like feature, right? Some gases are more subtle, and some gases, for say for these very faint targets, are going to be tiny, 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 tiny signals. So how do we build that threshold and that feeling in our tummy? Do we need to see it with our eyes to believe it? Or do we need to believe only our models? Where do we put our ruler as scientists to say this passes the sniff test and this one doesn't?
And I think the instinct with a powerful tool like this is to push to find its limits. And so you're not going to spend a lot of time enjoying these really robust carbon dioxide signals. You're going to go looking for the stuff that's at the very edge of what you can. You're going to find what those limits are, and that's where the arguments will shift to. So, based on what you've seen with JWST so far, where do you think those limits lie? Where do you think you're going to get to arguing over sigmas again?
I think the future of the field will be in the modeling territories. The war of the planets will be on the modeling land because the data is exquisite, and now we're building our models to the point where they are being challenged by the data. And that will be where we will be debating whether this is a capability that we're missing with our telescope or something that we're struggling with our telescope, or is this something that we're missing with our models? Are we missing sources of opacity? Are models incomplete? And that will be the really exciting shuffle that the field will be experiencing, I
I
think.
mean, could you give me like a concrete example of how that might play out?
Yes, I use this example a lot when I'm giving talks. I think that we are at the territory where we could have a headline in a year that says astronomers find a Six Sigma detection of cheese on the moon. And that will happen because we're trying to explain the composition of the moon with two models, a sponge model and a cheese model. And well, when you compare two models that are equally wrong, one of them will win. And you're like, well, I detected that the cheese model is preferred over the sponge model at 7 sigma. Therefore, I found cheese. So when we have incomplete physics, when we kind of lack a ground truth sometimes, you have a very complicated model with a biosignature and a very complicated model without a biosignature, and you just try to put them to the data. Well, maybe the one with the biosignature will, and you're like, oh, I found the biosignature. But that is just based on your models, right? And you are putting a lot of this Bayesian belief if the data is correct, this is what I get based on my model. But there's a big if the data is correct, and then the naive and truthful thing of, well, is the model correct?
Yeah, and I mean, this is a challenge that is as old as time, as old as computers, maybe before. Uh, what's the solution? How do you not get sucked into the beauty of your model?
Context, I think. And that is what I think many of us are pushing for in the field, is just bringing evidence based results through different metrics, through different profiles. So, do you see the bump? That is the first question. Yes or no? Okay, there is a bump. Is there anything else that could have happened in the data processing that caused that bump? Yes or no? Now figure out whether the bump is of astronomical. Well, that's the first thing. Figure out whether the bump is of astronomical nature or instrumental nature. Then is it planetary or stellar? And then you use models, right? And someone smarter than me once said that all models are wrong, but some are useful. So then let's use all these models and make sure that we can contextualize them based on their assumptions. If I assume that physics and chemistry works the way it works here on Earth, this is the solution that we get. And put that in terms of what do we know. So, for example, we could say that we found water on a planet. Fantastic. But then, is the amount of water that we found sufficient? And does it match what we have in the solar system? And then we can start talking about, I found something, it seems to be different from what I know happens here on Earth. And this is why I think it can happen. So putting it all out there, being very transparent, and bring enough context, both from the physics and the data, I think will help the community to move forward. And that is what I think we can get out of our modeling land.
Right. But I can definitely see that instinct that you've spent 10 years developing a model that if this, you see this amount of oxygen compared to methane in these ratios in the atmosphere of a planet, then that is a potential biosignature. And so you say you found a biosignature. What you really found was this ratio to oxygen to methane, and there could be a ton of different ways. And it's probably safest to say we don't understand yet.
Yeah. And personally, that is the cool sociological aspect of science, because almost kind of like what you were asking me earlier about, it's also important to publish null results. You need a little bit of a risk taker to say, actually, this may imply that we have found aliens, rather than hiding that result. Because through that conflict, through that peer review process, we will know whether that is true or not. So decoupling perhaps the science from the person, and decoupling the, ooh, this person wants to be the first one to claim aliens or win whatever fancy prize, and just say, let's put this in terms of what we think can happen, and let's work together, because astronomers don't have the answer by themselves. We need biologists, we need geochemists, we need the full field together of science to answer these very deep questions. And for that, there we will need to make these challenging claims, but let's just put the evidence out there. Let's make the data available and accessible for others to validate these results.
There are these, I mean, from the gases that you can detect directly in the atmosphere of your exoplanet, there are these indirect measurements that you can hope to make. One example being, for example, what's on the surface of the planet. You might not be able to see the surface of the planet, but your models might tell you what's going on, and because you're going to see certain gases show up in the atmosphere. Do you think, I'm trying to think of, are we ready to try to do that yet? Or do you think we should wait for more powerful telescopes? I guess you can't, there's no we and there's no monolithic and there's no should. I mean, people are going to try what they're going to try, right?
I think we should try it, and we may fail, and that will be exciting. I mean, I thought that these claims of aliens on an exoplanet were going to take us 5 years, but we've already seen some of those, and that is fine.
With the okay, right. I remember. I mean, just there was like that the Hycean world potential announcement.
The dimethyl sulfide.
Dimethyl sulfide, yeah, in the atmosphere of a world, and that's definitely jumping the gun.
It's challenging, right? Should they? It's when we get into the territory of the shoots, right? Should they or shouldn't they? So that type of science is being done.
I mean, I don't think you have to worry, because that's kind of my job, right? my job is to put things in context, to prepare people emotionally for when more information is coming down the road, but to not, because I mean, I think we want to show the enthusiasm that even the scientists have for the discoveries of these chemicals, and the implications are clear, but you can't say you found aliens. You can say we're really excited by the presence of this chemical, and we don't know how it works. And I trust my readers and viewers to be able to put this kind of stuff in context and not just start running around, emptying their bank accounts, stockpiling guns for the alien invasion, right? Like, people are going to have a balanced response to some of these discoveries.
And
you're
totally right.
Yeah, and I don't think scientists need to worry themselves too much about it, although I do know that you guys get blowback, right?
Yeah, and I think you're totally right. I think sometimes we get too caught up in the emotions of science, of like, ooh, is this result to be trusted, or what is going to be the impact? But then for me, the equalizer is when I talk to my family, and sometimes they don't even know what I'm talking about. They're like, what result? What do you like, aliens? No, it doesn't get to the point where we sometimes think that it gets to the point, right? But it's making sure that we know how to bring this into a lesson that will help us move forward. So perhaps this is a good incentive to investigate more the possibility that life may form in environments unlike Earth. I mean, that is a little bit of what the Haitian paradigm is pushing for, right? It's like, okay, well, maybe life can form in these environments. Okay, fine. Let's fund it more. Let's bring more money and more intelligent people to think about this, and let's see where it takes us. That is what I try to remind myself, to keep myself excited, even when I see results that clash with me intellectually or philosophically. And it's about their presentation sometimes where we disagree, but the science can still be robust.
Yeah, that's interesting. I mean, I think it's like when I'm reading papers, and I can definitely feel when the scientist is downplaying the excitement of what they've found because they're so nervous to be sort of seen as overly dramatizing what it is that they've found. And then on the other case, we all know of examples of people who talk too much or too highly of the results that they've found. And I think I prefer a scientist that does get enthusiastic and excited about what they found, but is able to kind of keep things and put it in context. And I think, it is a marketplace of ideas that what you found and what you're excited about has real ramifications on how much telescope time you get, collaborators that will find their way to you. It's a tough balance. I understand, and we do our part in this. Maybe we help or maybe we hurt. I don't know. So we talked about the potential of the surface can you can learn something about the surface of a world. Obviously, the big one is these biosignatures. So, what do you think is sort of the promising directions in thinking about biosignatures right now? Which models do you like?
Mine, obviously. No,
yeah, of course. Yeah,
of course. The big direction that we have already endeavored ourselves into is what's going on with these M-dwarf planets. And I suspect we will get an answer for that within the next 5 years. Within 5 years, we will know whether these planets around these very angry stars have or not atmospheres, and should we keep spending time on those. And from there, we will know whether, actually, we need to go find things somewhere else. Or actually, I'm making up statistics right now, but let's say that, yes, most planets are around M dwarfs, but only 0.1% of them have atmospheres and could be habitable by our standards. Then do we need to come up with a mission that will do a survey of M dwarf planets to figure out those that are habitable and overcome the challenges that we have learned on the way? That is our short term way, I think, of going about it. And our long-term way will be about procuring that information from several means. So let's have JWST, habitable worlds, whatnot, but also how can we bring more information from the ground? I'm particularly excited about the prospect of combining high-resolution ground-based spectroscopy with observations from space. So we can have two different telescopes look at a planet that we think could have a signature of life and get different data at different resolutions and combine that knowledge. I think that will be a very interesting way of moving forward.
Give me an example of one of these ground-based observatories that people should be keeping an eye on.
Yes, I think the first one to come online will be the ELT, the European Extremely Large Telescope. After that will be the Giant Magellan Telescope. I think that is slotted around the 2030s. And then after that will be the 30-meter telescope. I'm not sure about the timeline for that, but I'm just going to guess that it's late 2030s, 2040s. And beginning with the ELT and having just a big bucket of light with very high resolution spectra, I am excited about what that could tell us about the chemistry and physics of planets, the big ones, and how we learn to push it to very cold, small planets, cold by our standards of ultra Jupiter, so potentially habitable some planets, and using them to actually do observational campaigns. I think that will be our first opportunity to truly see biosignatures.
I can see why that's a very important fork in the road, because these planets around M dwarfs are relatively easy to see. You don't need that powerful of a coronagraph. That next generation of telescopes should be able to do these images, directly image these M dwarfs around, the planets around M dwarfs. And if it turns out that in fact half of them have atmospheres, everyone in the habitable zone has an atmosphere, like that gets really exciting. And
Yeah.
the engineering requirements to build the kind of telescope, space telescope, that can observe them all is different than the one that's going to have to go for the much harder worlds. But if it turns out every one you look at is a bare rock that's had its atmosphere blasted away by this horrible radiation and super flares, then apart from, the occasional fanatic who wants to keep studying M dwarf planets, the
Yeah.
field is going to shift away from them to the tough stuff. And you think we'll have an answer in 5 years? Someone, the community will say either M dwarves all the way, or we're going to have to dig deeper and go somewhere else.
Yeah, just by that comes informed by looking at what type of programs have been accepted from cycle 1, 2, and has 3 already been out? Yes, of cycle 2 of JWST, and what will come up for the next cycles is a lot of them were looking at the M dwarf planets, right? There are 2 programs looking at the cosmic shoreline and where do planets keep an atmosphere or not. And a lot of their observations have been taken. A lot of the results are currently presented in conferences. There are already some papers out, and I think we will have an answer of how difficult this is and whether we have a good opportunity with these planets around M dwarfs.
Do you have a guess?
I want to believe. I want them to be there. But
it would make life so much easier, right?
I know, right? But I am not optimistic. I think it's just a very harsh environment.
Yeah.
And I think that we are going to be, yes, if you crunch the numbers, it makes sense. You have a planet, but it's around a very small star, so the contrast is favorable. Boom, you're going to get a spectrum. But I think we underestimated, many of us underestimated the strong impact that the stellar activity was going to have. And we don't have really good models for M dwarfs. So how do we compensate for that? So maybe there's a very tenuous atmosphere, but it will not be as easy as just shooting at everything and getting all the observations and answering this question. I think it will take a lot of time, and it will not be as easy as we put forward with the M dwarf opportunity. And my non-scientific, I'll remove my science hat and I'll just talk as a fanatic of this. I'm just going to say no.
Yeah. I mean, there are so many strikes against them. I mean, you've got obviously a star that is capable of putting out oversized stellar flares at a regular basis that are more powerful than anything the sun can put out. Because the star is putting out less energy, you're going to have to nestle your planets close into the star. So it's like a double hit. It's the kind of damage that is perfect for ruining habitable atmospheres. The planets are probably tidally locked to the star. Like, there's so much going on, but what they have going for them is they're easier to see. They're easier to study.
Yeah, and if and when I'm wrong, and they actually have an atmosphere, and somehow these conditions allow for habitability, intuitively I would guess that they are not having habitable conditions like we have here on Earth, right? How do you create a world that survives all the things that you just said? It will have to have different balances and feedbacks, and if and when that comes, it will push us to think about life in the universe in a different way, and perhaps not be so central about our perspective as humans.
I mean, the hope is like maybe migration can solve the problem, that they spend some time farther away from the star and then they migrate inward after the star has had its tantrums, right?
Yes, sure. I think that could be a thing. I am excited about, let's get a telescope like Habitable Worlds that could look at less aggressive stars.
Mm-hmm. Well, let's talk about that then. Right now, the astronomical community is coming together to plan out the requirements of the Habitable Worlds Observatory. And one thing that I learned fairly recently is that the Nancy Grace Roman telescope has a prototype of a next generation coronagraph on it that its job will be to try to separate Jupiter mass stars orbiting around sun-like Jupiter mass planets orbiting around sun-like stars. So it's like a dramatically better kind of observation. So let's say that decision doesn't pan out. M dwarfs suck. There's really no need to look at them anymore. What will be the requirements for this Habitable World Observatory? What will be the requirements for this telescope to give you not just like a faint glimpse, but again, a strong signal for the kinds of things you're looking for in the atmospheres of these terrestrial planets around stars like the sun?
Yes, that is the $1 million question, and
Probably $10 billion
I
question.
yes, probably. I don't have an answer to that, and if I did, I guess NASA would be knocking on my door right now to take me to headquarters.
Well, I mean, it's not about like what's the solution. It's more like what are the requirements? Like what would you need to be able to see to do some productive work studying the atmosphere of one of those planets?
Yeah, instrumentally, I am not an expert, but obviously you need a very good coronagraph, and I know that. I mean, I'm excited about this project with Roman and testing these capabilities. How do you develop a coronagraph that allows you to block the sun and be able to distinguish something around the star at the position where Earth is? And how do you get that to be so precise and that you don't have any weird light interactions through patterns of refraction and diffraction? Um, I am I'm particularly happy to see, for example, star shades. I'm like, ooh, could that be really cool? But like, how do we push the science to get to the point where you can actually get things moving?
Yeah,
in
I
that
mean,
direction?
like, don't worry about it. Like the you'll ask the engineers, and they'll go like magic. We just did it. Here it is.
Okay.
But what do you need in terms of like the strength of the signal for you to be able to do meaningful science on those planets?
I see what you're asking. How big does the feature have to be in the spectrum, right?
Yeah, I mean, for when I think about Spitzer evaluating atmospheres, everything was we maybe probably think we could possibly be seeing something. Webb says it's just screaming carbon dioxide.
Yeah.
For you to give definitive answers on this telescope that's going to cost a lot of money, blood, sweat, tears of everybody involved, they're going to deliver this powerful instrument to you and say, okay, give us the answers. What will what will you need to see in your data to be able to feel pretty strongly about what it is that you're seeing?
I think I'm struggling with that question because we don't have a definitive answer on what life looks like, right? We don't have a combination of gases that we know that 100% for sure means life in another planet. I think that if I could ask the engineers to just pop their fingers get their fingers to work and give us a solution, it would be just like a picture, a directly imaged exoplanet around the habitable zone of its star. Just that we can resolve that. I think that would be groundbreaking if we could do that level of science. And then if we can get the spectrum, and we also compare that to the spectrum of what we know is happening here on Earth, and we see the signatures of oxygen and ozone and methane, and we have all these combinations. And even then, we will all be skeptical, but just by having the directly imaged exoplanet would be exciting.
But
To get, yeah.
I mean, I wonder though. It's interesting to me that you went straight to, I'm going to need to prove there's life there, and that feels like a big ask. Like I think that might be people's expectations, but I suspect that the scientists are really just going to be, we're going to study the atmospheres of these planets as hard as we can and produce lists of gases and move on and try not to make too many concrete pronouncements about what it is that we found. But obviously people can't help themselves.
Yeah, but we still want to have that answer, right? We still want to know
course.
whether there's life out there. And what will be the threshold that we have to meet, right? At what point can we as scientists be comfortable writing in a textbook, we have evidence that there's life somewhere else in the universe? And
Mm.
I I think that scientifically, if astronomers came up with a bunch of lines that we say that we agree, I don't know if our colleagues in the biology department would be happy to say that is life,
Yeah.
or our colleagues in sociology department will be like, well, but what is actually life? And
Yeah. I do.
that is
Right. I mean, that is the
uh, uh,
question, is that like, if we kind of still can't say what life is, it's really hard to say we found it. But you kind of know it
absolutely.
when you see it, right? So maybe we do. But I mean, this
Yeah,
is like dumb life. This is bacteria, maybe some kind of trees, plants. What do you think about technosignatures as a pathway for looking for life?
I think that would be the way to convince everyone in
Mm.
the planet that we found something else. Even so, I think of this as a series of things, right? We have a planet on the habitable zone. Check. We have a planet in the habitable zone with water. Check. It has ocean water. Fantastic. Then we have some inference of algae floating around. Fantastic. And we can just have all these little things and build bigger and fancier telescopes and observe this planet ad nauseum. But still, there will be someone somewhere that'll be like, but I didn't see it. Can you send a probe and like scoop a little bit of water, right? And we will not. And I personally think like, wow, what if we found a virus? The signature of a virus. I don't know what would that be, right? But technically a virus is not a life form. So we would not have found life. So we would get on all these conflicts and all these conversations. But truly, the only thing that could convince everyone is that we find it here in the solar system, in Titan or whatever, or that we get a technosignature, that we get a signature of their radio, of their TV, a happy little VHS sent to us where the little green men are saying hello, something that we cannot dispute with. And that will be a very high bar to pass. And that's why it's exciting to think about the future of science in that way. And technosignatures, I think it has a lot to offer, and it has been challenging to engage. And I have the utmost respect for people at SETI who are working on this non-stopping.
Yeah, it's quite heartening to see how well it's been embraced by the astrobiology community, by NASA, that they're actually starting to get funding to look,
Yes.
and even potentially time on Webb to search for things like chlorofluorocarbons. I mean, like, that feels like we're really turning a corner.
Yes, absolutely. I am so excited about it. And I hope that we have the maturity to speak about it in a scientific way, and that we don't have a cheese model with chlorofluorocarbons and then we say that we found chlorofluorocarbons.
Right, right. So, Luis, what are you obsessed about right now?
I am so excited about making the most out of JWST, and my next baby project is how do we combine this with high resolution spectroscopy. I am obsessed about how do we get the best tools in the planet and out of the planet, I guess, to work together and give us a cohesive picture of planets. To answer questions about the diversity, I think that we spent a lot of time talking about aliens, but aliens is just part of the picture. And I know that sometimes we say this just to like carry on with our funding and our science projects, but I fundamentally care about the diversity of planets. It is so exciting to see so many worlds and see how distinct and different they are to each other, and starting to see patterns in the population. I think the future of the field, I said it was models, but also when we have hundreds of exoplanets mapped out and say, ooh, there's this nice, interesting clump that have all this very interesting behavior, and we learn something about planetary formation. Think about it as populations. That really excites me. And so answering those questions through the combination of both techniques, that is what I'm obsessed with right now.
Yeah, it is interesting. Like, you see a lot of the most interesting observations are made using multiple instruments. You'll see stuff where it's like ALMA matched with JWST, and it's the capabilities where they overlap that you get some really interesting discoveries that are made, because you can see features in one wavelength that are influencing in another wavelength, and that tells you a new thing. And so right now, JWST is the only game in town to be able to make those kinds of observations. We've got Ariel coming out in 2028. As you said, we've got the extremely large telescope, which is just 2027. Like, we're just a couple of years away from this next round of tools that you can now bring them all to bear simultaneously on some target and, increase the amount of results.
And I mean, even now, this week there was a very exciting result about combining results from Gemini South, high resolution spectroscopy with IGRINs, with observations with JWST, and seeing how both telescopes agree. And when you combine them, they give you a more precise constraint on the chemistry of the planet. So JWST is fantastic and is giving us so much data, but then just pushing it forward with these telescopes on Earth and saying, well, they agree. And if we have something on Earth that gives us a picture of exoplanets, that also allows us to do more science, because that means that we are not shackled to an oversubscribed telescope. We can also do a lot of great science here on Earth, and that is an incentive to build bigger, better telescopes. And then there's several ways to answer these questions. We're not all limited to 1 point failure. Let's say, what if JWST blows up tomorrow?
Yeah.
Knock on wood, hopefully it doesn't.
Oh, that's interesting. So it's like you get so accustomed to seeing the signals of what it looks like in JWST, and you find those matching signals in, say, a smaller telescope. Then you can then use the smaller telescope to scan a lot of different places, and it's only then when you found like a really strong signal, you go back over to JWST. So it's almost like you've learned enough with JWST that now you can use other telescopes as a finder scope, now that you've calibrated the capability of the instruments against each other.
And it works also in the other way. Some studies have already looked at a planet with a ground-based facility, and they know that there's water, right? But by the limitations of the windows that we can observe here from Earth, we know that there's water. Okay, let's look for the carbon monoxide with JWST, and then we combine them. And the ground-based facilities, they allow us to have bigger telescopes with bigger instruments, and then we can do high-resolution spectroscopy, R of 100,000. So we get, not only do we see the bumps, but we now see this individual lines and how broadened they are by everything that is going in the atmosphere. So when we were talking about these very small signals for these possible habitable planets, imagine now that we can see actually the 1 or 2 or 3 lines that correspond to ozone. That will be outstanding. So going back, if I can convince an engineer to put a high resolution spectrograph on a space telescope, then that's it. That's how we win the game.
Yeah. So interesting. Well, Luis, absolutely fascinating to talk to you. Good luck with all of your observations. You couldn't have found the best field at the right time. You're going to have a very productive scientific career ahead of you, I'm sure.
Thank you very much. And I'm so happy to have talked to you.
I hope you enjoyed this interview with Dr. Luis Welbanks. Now, I'm going to talk some more about sort of my thoughts on the interview, but first, I'd like to thank our patrons. Thanks to Hey Twyla, Dougie Stewart, Stephen Krasaki, David Richards, Mark Ansis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Chiplin, Modso, George, David Giltonen, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Sometimes I feel a bit like, what happens when you get your wish? What happens when the scientific community puts an enormous amount of effort and energy and scientific research, and new telescopes come online, and their goal is to try to figure out if we're alone in the universe? It is a profound question, which would have implications for all of human society, the very future of our civilization. And yet it is a scientific question whether or not we're alone in the universe. You can go out and find them, and then you can know whether or not we are alone. And yet, because space is big and because planets are far, any announcement, any discovery that's made is almost by nature right now inconclusive. And we've seen in the past how people can take inconclusive results and they can argue about it. People maybe have announced their results too early, and that casts a long shadow over the entire field of astrobiology. And yet we have these incredible tools. We have JWST, we have ground-based observatories that are coming online. Each one is going to add its energy to answering this question, as well as all of the scientists who are involved in it. And yet there is a greater responsibility to be sure that whatever you say you found, you can back it up with science, that it will withstand scrutiny. And it's a weird time to be existing right now, when we are before this question has been answered one way or the other. And we're going to watch it play out and unfold. And I think all I recommend is patience, that this question, this is a mystery that is going to require an enormous amount of work from everybody involved, from the engineers designing the instruments to the scientists doing the studies. And they are going to present the results, and they're going to be nervous about what it is that they say. Like, unless the alien fleet is approaching and is orbiting planet Earth, everything is going to be inconclusive. And so we have to put everything into context, take our time, and be excited about the journey, not necessarily fixated on the destination. And that's where I live now, is enjoying the journey. All right. I've done a ton of interviews very recently that match this topic. And so I'm just going to link randomly to 2 of them here. And I know you're going to enjoy them. All right. We'll see you next time.